Okay, we're on to Chapter 6, the skeletal system. We're going to describe the structures and functions of the skeletal system, particularly the structures of long bones and bone tissue. We'll describe the formation of different types of bones and explain calcium homeostasis. Okay, the skeletal system is needed for support. It forms structures which other systems depend, like the rib cage, which is needed for the respiratory system. It also protects underlying structure. Our most delicate structures, like our brain, are usually protected by bony enclosures. The skeletal system is also crucial for movement. The shape of the bones, the joints determine whether movement is possible and the type of movement that will take place. The skeletal system stores material, particularly calcium, but also phosphates and fat. And these are important in maintaining homeostasis. And so we'll talk about calcium homeostasis. And then one tissue in the skeletal system is responsible for the production of blood cells in the adults. These include platelets for blood clotting, immune cells to fight off infection, and in particular, most importantly, red blood cells for oxygen transport. Okay, the skeletal system is made up of a bunch of organs that are formed from several tissues. The most common tissue is compact bone, but there's also spongy bone. Here you can see in this shoulder joint, the edges are compact bone, which is quite dense, and then spongy bone, it forms that network in between. But there's lots and lots of other tissues, fibrous connective tissues, fat tissue, adipose, several types of cartilage, lots of blood vessels and nerve tissues. Of course, the most common tissues are the bone tissues, compact and spongy bone. Up here you can see compact bone at the top with lots of matrix and few cells. Spongy bone forms these ridges or trabeculae. The bone matrix provides the hard structure of the bone. This contains both organic materials and inorganic. For organic materials, this is collagen, the protein collagen, and some proteoglycans. That's proteins that have sugars attached. They provide some flexibility. The inorganic material are calcium salts, calcium phosphate crystals in the form of hydroxyapatite. This provides the solid structure. It's quite brittle without the organic materials, but it's with them both, it's strong, slightly flexible, and resists breaking. Okay, as I mentioned, the bone is classified by the amount of matrix relative to the space present. Cancellous bone or spongy bone has lots of spaces. It's lightweight but strong, and these trabeculae are these kind of reinforced network. And inside the trabeculae will be marrow. The compact bone is very, very dense with few spaces. Okay, so here this shows the compact bone. The circular areas with the rings around them, those circles are lamellae, the circle of cells, but the central circle is where you would have a blood vessel. These are the canals, the Haversian canals or central canals that are arranged around the blood vessels, and these little spaces are lacunae, and they have the cells in them, the osteocytes. Those osteocytes will be connected to one another by tiny little canals, and so they'll exchange materials. Bone is solid, but it's a living tissue. Compact bone is usually arranged with these blood vessels running the length of the bone and then these circular rings around them. This is called lamellar bone. Most of the collagen fibers are oriented parallel to these blood vessels. And sometimes the collagen fibers are oriented in different directions. This is woven bone, and woven bone appears generally after a fracture, so after there's been bone repair. Okay. In cancellous or spongy bone, these lamellae look slightly different. In this case, there's no blood vessels inside the trabeculae, but these trabeculae have cells in them that are connected by these little caniculi, and then most of the osteocytes and osteoblasts, the bone-forming cells, are located on the edges of the trabeculae. And this forms a branching network that's lighter weight but still strong. Okay, bones are classified by their shape. There are long bones, short bones, irregular bones, flat bones, sesamoid bones, which are bones that form in tendons. But long bones are the only ones I'll have you kind of look at. Long bones are the bones like of your arms and legs and most of the bones in your hands. These bones have a long hollow shaft called the diaphysis. The hollow space inside the shaft is the medullary cavity. It will have blood vessels in it and fat. That's what we call yellow marrow. On either end of the bone, you will have the epiphyses, and these will be covered by articular cartilages, which will be forming in the joints. And then inside that epiphyses will be lots of spongy bone and red bone marrow. That's where blood cell formation takes place. Okay, and then there's a membrane that surrounds the outer part of the bone. It's a fibrous connective tissue. The periosteum contains the cells needed to repair bones. And there's an endosteum, a little membrane inside the medullary cavity as well. And then there's a growth disc or plate if it's been replaced. Here they show these growth lines. That's where the epiphyseal disc will be. It's a cartilage plate in a growing bone. So let's show you that. A growing bone. There are two types of bones as far as formation goes. Most bones are cartilage bones, which these form early in the embryo as a cartilage model. And then osteoblasts, these are bone-forming cells, invade in the center part of the bone, the diaphysis, and they form an ossification center. Okay, and that happens in the center of the bone, and it starts moving outward or towards the ends of the bone. And then there are secondary ossification centers that form in those epiphyses, where the epiphyses are, and cartilage will be between those primary and secondary ossification centers, and that's about the way it occurs at the time of growth or at the time of birth. That the bone will have this big cartilage plate in there, and that epiphyseal plate will be called the growth plate, and it will remain cartilage until your teenage years are done, or your puberty years are done, and then it will be replaced by bone, and there won't be any more growth in length. Okay, the other type of bone are membrane bones, and these include most of the flat bones, like our skull bones and maybe our clavicles. And these form in connective tissue layers below the skin. And just like in the cartilage bones, osteoblasts will invade this connective tissue layer below the skin, and they'll start producing bone matrix. But here they'll produce trabeculae, and then around the trabeculae you'll get compact bone developing. And this will start in a central area and grow outward towards the end of the membrane. Okay, at the time of birth, this is not done very completely. There's lots of membrane space in the skull. These are the soft spots of babies. And those bones will gradually grow together until the amount of membrane between them is relatively short. Okay, but in the skull, that little bit of membrane will remain there until their late teenage years, again, the end of puberty, when it will be completely replaced by bone. All right, so we're going through some topics really fast here. The last one is calcium homeostasis. Bones store calcium, okay, and they maintain a very important role in homeostasis, maintaining normal levels of blood calcium. Calcium is really important for a whole bunch of things. Particularly, muscle cells can't contract unless they have adequate levels of calcium, which they get from the blood. This is not just your skeletal muscles. This includes your heart muscle and your smooth muscle. Likewise, nerve cells can't send messages unless calcium levels are okay in the blood. And so these are really crucial, absolute requirements. And homeostasis is to maintain normal levels of calcium in the blood. Okay, here the control centers are two glands, the thyroid gland and the parathyroid gland. These are in your neck. The parathyroid glands is actually 4 little glands that sit on the back of the thyroid. If calcium levels drop, these parathyroid glands release parathyroid hormone, PTH. And PTH has 2 or 3 roles. It will increase calcium uptake in the intestine as long as vitamin D is present. It'll reduce calcium loss in the urine, and then it'll increase calcium release from bone. Cells called osteoclasts will respond to this hormone by breaking down matrix and releasing calcium. And calcium from bone is the fastest way for us to get calcium. So in the short term, that's fast. The other mechanisms take a little longer to work. So this will cause calcium levels to rise back to normal. If calcium levels are too high, like we've just had a meal with extra calcium in it, the thyroid gland will release calcitonin, and this will cause calcium to be stored in bones, so new matrix will be deposited. It'll also decrease the uptake of calcium in the intestine, and it'll increase the loss of calcium in the urine. Okay. These are, again, good negative feedback mechanisms, but notice how fast calcium can be added to or taken from the bone. That's a quick, immediate way to change calcium levels. The other mechanisms are slower. This is really important because calcium is needed for bone growth and bone remodeling, and I'll say more about that later. But these 2 cells, osteoblasts deposit new matrix, osteoclasts remove matrix, and they're always active doing this. Okay, if calcium is insufficient in the diet to build up adequate bone matrix, it may be that osteoporosis results when you're older. This is an important problem for over 20 million Americans, causing 1.5 million fractures a year, including fractures of the spine, the hips, and the femur. And what happens here is that chronic low levels of calcium cause calcium to be removed from the bone continuously until the trabeculae within the bone become weak and the bone can fracture spontaneously. This is very serious, and it's more of a problem in older people because they are less able to absorb calcium in their diet. They're less active, so there's less stress on the bone and reduces the amount of material put into bone. And because hormone levels drop, particularly sex hormone levels in older men, but especially older women when they go through menopause, those hormones affect the osteoblasts and make them less active if they're not present. And so this is a major cause of fractures. And here this lower diagram shows the compression fractures of the spine. The loss of height that you sometimes see in older adults is due to fracture. The spine actually compresses. Very difficult to treat. Okay, so and this again happens can happen in the femur, can happen in the pelvis. So really, really serious. Normal bone has substantial trabeculae. In bones with osteoporosis, those trabeculae will be almost gone. Okay, I'll have more to say about this in a forum, and we'll talk about it then.